towards exascale computation of quantum system and industrial perspective. So, ready to fly? Okay, go ahead, please.
Okay, so thank you for this kind invitation. And, okay, I just checked that so that we have lunch, I guess, after my talk. Oh, we can skip lunch. Okay, so thanks again. And I would like to give you a little overview in this next 20 minutes about what we are working and also how industrial perspectives comes into this topic, and then the kind of industrial collaborations, and now what we are working on together with many companies. So, and also this work is done, as you can see, usually I'm half of my body is in Germany. I'm having these German affiliations. I'm also working a lot in these other places. And so we are developing some computer code for almost 30 years. They can still do it more than that, but it's really used worldwide by some 30 research groups in many areas of physics and chemistry, applied mathematics and computer science. And in the past years, we put a lot of efforts also to pushing things on high performance supercomputings, and these things I usually do in Germany, in Stuttgart, also in Örs, in the supercomputer centers in the US. And what is something is that at the beginning, some around 2002 and 3, where we wrote papers about mathematical scalings of this method, for us, it was obvious that in maybe 10, 20 years, this is going to be the leading method. So it was not a question because of the mathematical properties, but somehow the scientific community okay, so the scientific community is difficult to convince them just based on mathematical formulas. So you really have to provide applications as well. And now we are in the stage that we can solve problems which is unsolvable by all the other methods. So now people start to listen, oh, this is good, now we need it. And so now everybody would like to have this immediately, just put it into different codes and so on. And in this very recent work that we had, that's also the industrial partners also got their interest and attention. So now we have direct collaboration with NVIDIA, Sandbox, which is a Google startup, and also Riverlane, that's a UK startup company, Furukawa, that's this company from Japan, also doing lots of research and innovations. And this is my company in Hungary. Okay, so that the basic idea is that when we have electrons and then they move, I just give a little introduction, then of course the correlation, the interactions between the electrons can generate new kind of phases and a new kind of material properties. And the simplest one is this high temperature superconductivity, where we all know that if we change something, then cool down the matter, this material, it becomes superconducting. So you can pass energy without loss and so on. There are many, many interesting properties. So this is in the focus of physics, of course, to simulate and study such things. And nowadays you can also have something like single molecular magnets, which you can synthesize so that even molecular level you can have some spins. So this is artificial stuff, and also in battery technology, we all know that this is very hot issue nowadays to have all these new materials and so on. Now it's very expensive to do all these things in labs, so that if you can do the computer simulation, just like now, if you have AutoCAD and you develop something like you design a new car or an airplane, you don't build millions of models, but now you use all these CAD-based simulations, and of course you can save a lot of money. And I will also focus a little bit this because that's also in nature, which we work a lot, and that's basically how to capture the atmospheric nitrogen and convert it to ammonia, which is crucial because we have now 7 billion people in the world, and this is only possible because of the agricultural background, and that's all based on ammonia. So if you can understand that how this is done in nature, then maybe we can learn, and so that maybe we can reduce the cost of generating ammonia, and that would, of course, tremendous impact in our society. The other issue is that what we can do is, for example, these so-called ultra-cold atoms, that where you have something like a box, and then you have some lasers, which has some waves, and in the minimums of the waves, if you put atoms and you cool them down, then they get localized in a nice structure, and so that they form a lattice. So these are real artificial materials that you can simulate in this optical lattice systems. Mathematically, this is this formula that we write down, that there is an electron in one lattice point, and it can jump into the other. And since there are electrons with up and down spin shown by the red and green, if they are on the same side, you pay an extra energy. Okay, this is this model. And the idea is that you would like to get these quantum states with some computer simulations, and the question is whether to use classical or quantum computers. Okay, and now today I will focus on the classical aspects, but of course the algorithm that I'm showing, it's also a kind of simulation of quantum computing. So without getting into too much detail, but maybe some of you are not in quantum physics. So let's say that you lay down on the floor and then you just stand up. Your change is continuous, so that you have many different phases if you just take a picture from different time steps. But of course, you can restrict it. So maybe there are only 3 states. It's possible. This is what we call this tensor space dimension is 3. And if you put n persons in a room, then the scaling is 3 to the n, because all possibility and all configuration must be included. So that's what we call that this scales exponentially. Now, the big difference between classical and quantum physics is that the superposition is also possible. So that it's possible that there is a person A and B, and one is in state 1 and state B, like stand or squats, or in the other one squats and stands. And this gets only probabilities, so that you add up all these things, and then there is some coefficient in front of this, and that's basically the superposition, so that all these are possible. That's basically the big jump compared to the classical physics. And in physics, this is what we label like spin up and down, get mixed with the down-up states and with these things. And that's what we call entangled states, and that leads to quantum information science. And this is exactly what happens, that when you have the 0 and 1 bits, and then you just mix them together with some coefficients, then you can have this so-called qubits, which is a superposition in a combination of the 0 and 1. And just like in normal classical physics, where you have circuits, you can also have quantum circuits and can do many things, and then on the quantum states. And that's basically, there were many talks already in this direction. And of course, something that we would like to have like quantum supremacy, that means that the quantum advantage, that can we solve some problem which is solvable only in a reasonable time, only by quantum computers. To be honest, at the moment, there are always some papers from time to time claiming this, but we have not reached this yet, because there are always some contradictions from the classical simulation community showing that the claim was not really true. So we are not at the stage yet to really have this proven, but there are these 2 main directions to really push things. Okay, what I will focus on, it's just simply that this quantum many-body state, as you said, that these are the persons that they can stand or sit or squat. So these alphas just label these states, and then you just take all these products. These are the number of people in the room, and there is this coefficient tensor that I mentioned, this probability. And you would like to get all these coefficients, so you would like to solve this, and that's what in mathematics we call this is a tensor, which has as many legs as many persons in a room. And this is something like what is called the eigenstates, the ground state, excited states, and so on. And the take-home message is that if you have a tensor which has many legs, you can always factorize it as a product of tensors, where you have a smaller number of legs, but these are connected with some lines, and there are some summations which we call contractions. So the idea is that any of these high-order tensors can be factorized as a product of lower-order tensors. And now immediately you can see this as a structure. So this is what we call tensor network states and tensor network simulations. And of course, the arbitrary choice for the tensors, topology, and everything. So this is very important. You do math, choose to find optimal representations and things like that. But once you have this, you can do all these different constructions in parallel. So that's a completely ideal work for HPC parallelization. That's how this goes connected to the GPU day-to-day. That you can also get this simplest representation, where it's just simply product of matrices. But important, there is the scaling, which is the rank, which is the number of non-zero elements in this. There's the number m, and the scaling of this algorithm is m cubed. So this exponential scaling that I mentioned at the beginning is already reduced to a polynomial form. It's m to the cube, so we are very happy. And in the past 20, 30 years, there has been many works in physics, chemistry, and so on, using this algorithm. And for example, just write down if you have a molecule, and then it's just isolated by some quantum information based quantities. You can show that how the molecular orbitals are correlated, how they are coupled to each other. You can also show that which molecular orbitals are the important. Or if you embed this into an environment, so you just put something around it, then this profiles, of course, change. And so that you can also see that how in some chemical reaction, what happens, and then what are the interactions, and what's the effect of the environment, and so on. And this is completely arbitrary. Okay, now this is the connection that, as I said, that all these networks you can do independently. So let's go for HPC parallelization. And we already had a very early paper in 2014 to put everything on the GPUs. So that basically the algebra, all the tensor and matrix algebra, decomposes into millions or several millions of independent tasks. So this you can put into parallelization. And we already used this on GPU on K20 cards in 2014, but that time the performance was really limited. So it's a bit faster than Xeon processor, but of course there was not a big game. And then, of course, we had some MPI parallelization, just that where we showed that with the number of CPU cores, the time is more or less the wall time is a linear function. And that time, around 2015, 16, this was the big announcement that a supercomputer center in Japan, it's over 10 petaflops. So it's a huge number. You understand to the whatever, I think it's 9 and so on, or 12. And so everybody was, oh, so actually it's even larger. It's I think 10 to the 15, sorry. So this was the biggest one. So keep it in mind that 10 petaflops in 2016 was a big number, okay? And now, can we do something more? And of course, we can use larger machines. We can do many other things, but that's basic on the hardware. But can we do something also, some clever stuff on the software side? So by that software, I mean something about rewriting parallelization ideas and so on. And so as a cartoon, I just gave also a public talk. So that's why we have this here. If you have a society and there is an aim that you want to build a pyramid, this is a very unhealthy society that there are the workers which are just packing things. There are some which transports the data, and there are some which execute the data. And these basically, you can see that there's a one-to-one mapping in this kind of computer science, and there's a central scheduling. So usually there is a central scheduling, and this is the one which schedules all the work. But this guy is the only one who knows the final aim, and all the others are just working. And of course, he has to force everybody to work. Okay, so it's pretty nasty. And of course, there's a huge overhead and load on this guy because he has to organize everything. Okay, so, and of course, he cannot see everything. And those who are not in his view, they can be in idle, so not doing anything. Okay, just having fun. And so that, of course, then there's a huge overhead, plus, of course, it's an inefficient scheduling task. But what if we change this, and then we go to a more healthy society that everybody is doing their work, and there is a guy in the center, but he's not forcing them to work, but he's just the contractor. So there are some tasks and threads and computation units which generates the different matrix and tensor algebra components, which just has a Boolean flag, just put something that, oh, we have generated some task. Of course, there are some which transport it. So basically from something like between the GPUs or CPU, GPU, or between the different nodes and so on. So this is why you have these different kind of tracks, of course, because the bandwidth is different. You can have, of course, different set of tasks. And then there are the guys which execute. And these executors are what we call, as I will show you, maze runners, which just simply look always for uncompleted tasks. And they complete the task. And once they are getting idle, they look immediately for the next one. Okay, so that no one is in idle. It's a 100% load on everybody. It's a full power of utilization, plus it's fully scalable. So this is what hopefully in the future for exascale, and I will show you that how far we got with this. So that's basically the idea. And also you can have also bigger tasks where it's a collection of several tasks. So it is also possible that this guy checks out a big box, which is composed of many tasks, but these are already ready. Then they can also ask for tasks. If this is already out of any further ones, then they can get and steal some from here so that there is also distribution of tasks so that everybody is fully dynamically scaling with all these things. And this is what I was working a lot with Andor. And Andor implemented many of these things. And here we have the talk in the afternoon going into the details, but just keep it in mind that we have this new parallelization model in math, these maze runners. Also, it's very important that how memory is managed in the CPU and GPU side. And if you just simply use the NVIDIA malloc functions, there's a huge overhead so that it's very inefficient to transfer the data or move the data several times. So we have now a graph theory-based memory management. We don't use any CUDA libraries for memory management, but we have our own libraries where you traverse through these graphs and you identify that which data sets are needed more than once. And then you execute everything that is related to a given data sets and you transfer only those which was not used yet so that there is a limited IO. And with this way, we managed to hide the IO, transferring the data from the CPU to the GPU behind the computation. Also, there's a lot that how the data is stored, that whether it's a continuous segment in memory, you can also change many metadata and so on, so that you can use this threaded version and then the version. And all these just boost the performance that I will show you. And as I mentioned, also there is how the tasks are executed. Therefore, you have this hierarchy of tasks. And we have many algorithms that how to get the task from the contractors, how to steer from one to the other, how to split it, and all these things. So everything is completely dynamically scheduled. And some results that we had last year, so that we took something like a chemical system. This is the F2 molecule, where you have 18 electrons and 18 orbitals. And the reason I chose this, because this is the current edge of supercomputers to doing this problem in exact way. So that if you want to solve it with an exact diagonalization, this problem, this is the cutting edge. You can do 18 electrons and 18 orbitals, and that's it. You can go any further because of the exponential scaling. Now, if you use this mathematical scaling, then you can go further. But before that, I show that this is what we had. This is the performance using already 8 GPU cards. And so that's basically that as we increase this D value, as I said, the scaling is D to the cube. So we just simply increase the matrix sizes. And this is the performance. Now it's already in teraflops. Now keep it in mind that one node with 128 cores, that's about 3 teraflops. Okay. And now we are up here, something like close to 76 teraflops. And that's what is called NVIDIA FP64 limit. So that if you use the FP64 representation and 8 cards, then it's basically 8 times 9.8 teraflops. So this is how you get this 76 teraflops limit. And this is what we have reached. Now it's funny because you can see that we have also some above this. That how could it be? That how could we get better, performance than the theoretical upper bound? That's because this NVIDIA also offers you this so-called tensor core units. These are these very special AI accelerators, so that if you can write your algorithms that also utilizing these units, then you can go up to 150. So that's basically the theoretical maximum from NVIDIA, 150. But the largest benchmark that has been done by NVIDIA, they managed to get only up to 142, so up to here. Okay, so that's really the measurements that they did. And now we are here about something like 110 or so. And also, you can also use symmetries, which means that besides those who knows that you can also use them, not just the particle number symmetries, but spins and so on. So this is what is called non-abelian symmetries. And if you work hard, then you can do this also, all this mathematical formalism. And so that you can rescale that what would be the performance if I use also this. And I wouldn't use it, but simply U1 symmetries, then the problem that we solve at this stage exactly would be this solution without these extra symmetries, and that would correspond to an effective 300 teraflops. So that if you don't use all these mathematical tricks, you need something like 300 teraflops. Now, if one machine is 3 teraflops, then you can see that this is 100 nodes, each with 128 cores. So it's 12,000, I don't know how many nodes, cores that you need to solve this problem. And that's cool, because now this point represents to this exact solution, but getting it only in polynomial time, so that we can do this exact problem with this, what is called the exact solution, so that we can now really get the same result as with the supercomputer, with this full memory need and so on, with this algorithm in 7 minutes, while in supercomputers, this problem in the original representation runs for a couple of days. Okay. And that's exactly because the exponential scaling is back to the linear scaling plus with parallelization. Okay. So let's go for the next one. Okay, now we can go for much larger system, and that's exactly this FEMOCO, which I mentioned you that this is this converting the atmospheric ammonia, nitrogen to ammonia. So this is this kind of thing. This is why I'm also doing a lot of work on that. And here we went up to something like 113 electrons on 76 orbitals. This is very large. As you can see, the 80. Now we are here. And so that here we went up to almost 120 teraflops in performance. And now NVIDIA said, oh, this is super, because if you send just a simple matrix multiplication to NVIDIA, then of course you can use a DGEM or whatever, or CoolGEM and so on. And therefore you can do this. But now it's a sequence of more than 1 million or 10 million independent matrix multiplications. And that shows you that we have a perfect scheduling algorithms together with hiding the IO. So they said, oh, this is super cool. So now we have this collaboration with NVIDIA. Also to putting our algorithms now to H1 performance compared to the A100s. And now we are also working now on the GH200s. So this is going to be the next generation from NVIDIA. And I'll show you in a second that what is it. And so that now I'm already having an account in they made me an account in Amazon server and some of these Google clouds where I have access to these H100s. And also now we are working on the GH200s. So the paper will be out soon. That's we are about something like 240, 300 teraflops already on a single node. And if you put this together, then it's easy to say that even if we reach here with 120 and then we just put together 10 nodes, we are immediately about 1 petaflops. Okay, and this is where we are now with Andor. So that now we use 16 nodes already together. Each we do these 8 A100 cards. The paper is not out yet, but hopefully in the summer we will have it. And so that this is going to be this petaflop scaling. And now, of course, if you can scale it up and use 100 nodes, then you can go up to maybe 10, 100 petaflops. Going further, we need further design in memory distributions and millions of other things. But just because of this whole ideas about all this dynamic scaling and polarization, I'm pretty sure that in a couple of years, the exascale is really not a dream because everything is scalable. So this year, we want to go up to this couple of petaflops. And of course, later on, if we use this before that, I just wanted to show you that if you do the polarization, then this d to the cube scaling as a function of this rank. If you do the time, if you measure the time and then you do the polarization, you can see that because of this very big increase in performance, you can reduce this d to the cube scaling. The exponent is really 1 or 2 here. And once the saturation of the GPU cards are reached, then of course you recover back the original d to the cube scaling that you can see here. And that's exactly what happens here. So here, as you have this very fast increase, but here you get this saturation, of course, because that's the limit. You cannot get out more performance from a single node. So then that is why we can do these calculations now in order of hours and not order of week, because of this exponential scaling is back to polynomial. And now the polynomial exponent d to the cube is back to d to the 1. So this is really going to revolutionize all these quantum system simulations. And now if you go to petaflops, then there is going to be immediately a factor of 10 to 20 increase in performance. And just as if you are working, let's say, in two-dimensional system, as I said, that in these quantum lattice problems, you can also do the simulations. And what we had a recent paper is that there are all these mathematical scaling and issues that you can derive, but now we measured all the matrix and tensor operations in flops. So it's really what comes out from the computer. If you plot it on a log scale, you can get these very nice lines with an exponent 3. And therefore, we also reduce somehow some other mathematical tricks, also the computational complexity, so that we show that some scaling can be also changed as how the problem scales with system size. Also, there is a big reduction. So now, what is nice is mathematics is directly related to computer science because everything is measured just in flops. So there is no cheating. This is exactly what you get out from the machine. And that's super nice because now that's I would like to have also enforced in the future for all these numerical simulation papers that people should also present their flops also data because that really confirms whatever you claim that you achieve that could be directly measurable in terms of flops, and so that you can also show the scaling equation. Okay, and this is exactly this GH200, as I mentioned already. This is going to be this new generation. And what is amazing is that in these cards, you have CPU and the GPU on the same bus. So this transferring data from the CPU to the GPU by PCI Express, you can avoid this. And this is super fast. It's 900 gigabits per second, whatever. So it's a super fast NVLink. And everything is connected to everything up to 256 GPU cards. This is super expensive. What is the most expensive part of this new super chip is basically the connections and then the data transfer. But then single chip can have over more than 1 petaflops. Now you put together 10 of these, then you are immediately 10 petaflops, and then 10 of these machines is the same performance as was in Japan, the K computer in 2015 and 16. So it's amazing. It's amazing what is going on now. And this is not the end. And now AMD has also the same kind of chipset, which is called MI300s. And that's exactly, I was last week in Toulouse, and then I discussed with Gergely that I will mention a couple of words about that. This was a special SICAM workshop that was organized only attendance by invitation. So they invited the representatives from AMD, Intel, what was the AMD, Intel, NVIDIA, and for many companies. And the idea is, as you see, that many people are doing this matrix and tensor algebra. We were developing different things, but can we push these to the vendors? So like in BLAST, LAPACK, MKL, there are these standardized matrix libraries, but there is no such thing for tensors. So this 1 week workshop was that we were split into groups of, I don't know, 10 of us in a group, and there were given topics, and we all had to work on the different topics. At the end evening, we merged it, and we went through. And the idea would be the vendor should also provide these tensor libraries, just like MKL and BLAST and LAPACK, because it's going to be, of course, much more efficient because they have already the freedom to design the internal structures, how data is passed in within the chipsets and so on. And that's basically something that just started. And there's going to be, of course, many things in the future. But I'm just saying that also there's a big effort from industry to really to push things because at the moment, there is no other way to simulate these quantum systems such an efficient way just by these tensor algorithms. And that's how I just conclude my talk. So that you need tensor network methods, you need this concept of quantum information theory, as I already briefly mentioned. And you need all these AI-motivated hardware advances. So the reason what is happening that everybody's talking only about AI. Oh, AI. There is nothing else. But there are many things besides AI, and nobody's talking about the others, but only AI because it's just a big. I mean, people can understand. Oh, we create something that is more intelligent than humans. Then of course, it's everybody can grab this message and so on. But if we can jump on all these developments, then we can utilize all these things for us also in other fields than AI, and that's exactly what we were at the right time at the right place. And now there is a current work that I'm just working, and this is some results from last week, or actually I did this over the weekend. So you remember I said 18 electrons on 18 orbitals, and now we are 536 electrons on 1,368 orbitals, and that's doable. And now all quantum chemistry methods are outperformed. So all the quantum chemistry developments in the past, I don't know, 50, 60 years to solve these strongly correlated problems are basically outperformed by this method. Of course, you need all the knowledge from the Quantum Chemistry Society, and that's basically why we have this ORCA program package where all these quantum chemistry related things are implemented. But we provide this TNS solver from this so-called DMRG, which is just a tensor network algorithms, and the two together gets you this. So it's very important that the new things must be always combined with the older stuff and take all the knowledge that has been piled up in the past years and so on. And I thank you for your attention, and also different grants and support. And of course, I have to mention also that as a benchmark, also some of these calculations were also performed in the VSC lab. For example, that's usually we need a dedicated time because we really use the full power of this machine, which in the VSC lab, we have this one machine with 8 A100 cards. And actually, it is even faster than what I have in Stuttgart, because here it's only one node. So all the PCI Express buses are allocated to GPUs, while in Stuttgart, cards are for the GPU and another for the multi-nodes. So in this case, of course, we were faster, and we were happy to show that you can even boost it further. But nevertheless, it's a super great node, I must say, and very strong. And it's very good to do also this kind of test. And of course, when we have to run, I don't know, 10 to hundreds of simulations, and that I have to do in Stuttgart, but to calibrate things, that's very important. So I thank you very much for your attention.
Thank you very much. And I really appreciate to give this short summary on Netulus workshop. Okay, time for questions. People got time, please.
Yeah, thank you for the great talk. I have a sort of theoretical question. So sometimes I can read stuff like a certain quantum circuit is efficiently simulable by some MPS or MPO simulators. And so my question is there like a bound on the bond dimension scaling, or above which we cannot call it efficient anymore, or how is this defined?
Yeah, thank you for the question. Yes. So coming back to this thing, so these quantum circuits are another way to simulate this quantum system, which is exactly in the same tensor network structure as you have seen. Usually people do simulations, most of the simulations in this range, 1,000, 2,000, 4,000. So now that we go up to 20,000, or here we went up to 2 to the 16, that's 65,000. This is the largest calculation that has been done. So that if you can use the polarization, then there is no limit on bond dimension. You can really go up. Of course, you don't have to wait for weeks, but you can get this, in reasonable time. Plus, if you distribute your data on these many nodes, then of course, you can also solve the problem that increasing the bond dimension. Of course, you need more and more data to store, all the matrices get larger. You will hit the memory limit of your computer, but in the case of distributed architectures, of course, you can go up and scale it up. The big question is always the I/O, the communication. So the big thing that you really have to work very hard is to find out that how you could hide the I/O behind the calculation. So you would like to keep everything for the computational complexity, just really do the algebra and hide everything else behind it. And that's very crucial, and that's why we need all these kind of tricky ideas and many other solutions.
Thank you.
All right, don't you have a question? Thank you for the great talk. There is a saying in numerical circles that understanding only grows logarithmically with the performed floating point operations. So you have shown these nice scalings and the number of electrons and orbitals that you managed to put into the calculation. But overall, how much our understanding of these quantum processes that you showed at the beginning have improved by scaling all this stuff up?
Yep. that's of course my time was limited, so I didn't go into simulation of quantum computers, but these kind of things. And also I also updated my talk, but the one that is on my notebook, so I just this slide I forgot to include when I sent in the morning. But anyway, I also had one slide about connection of tensor network methods with machine learning and deep learning, because exactly the same tensor structures used also in deep learning and MI. And also, as I said, as you say, that there are these quantum circuits, and there are many things. For example, there was this Google paper 4 years ago where they claimed quantum supremacy, that they used these quantum circuits. There were some gates, 1 qubit gates, and then there were 2 qubit gates, and then with some simulation of some problem. It's an artificial problem. It was not good for anything, but they just wanted to show that in this problem, you can really get this quantum supremacy. And the paper came out, and then I think 2 or 3 months later, Maya Studemeyer from this MPO, this tensor network community, came out the paper showing that what they claimed that you need, I don't know, 10 to the what, 10 years to solve the problem. He did this in, I don't know, in 1 month. So because reducing the exponential scaling back to this one. So the question is that if your problem can be grabbed now in this region, then you can see that you can utilize this linear scaling, and of course you can go for very large and very efficient simulation. Now, you hit it because at some point we hit this one node, but if you combine now with the several nodes, then of course this line can be continued, for much more and so on. Okay, and so basically the question is also that if you have a problem, let's say 10 to the 10, here's by the way the Hilbert space dimension that I wanted to, somewhere I had the, and exactly it's here. This is the original problem. This will be 2.88 times 10 to the 36. So this is the size of the problem that we solve now, and you can see here this exponential scaling. So that if your problem is a question, do I really need all the persons, all the components in the room that finally affects the outcome? And then this is why we use the quantum information theory-based stuff, because it turns out that maybe in the discussions, only those are important who are around the round table, and all the rest are just simply listening to what they are talking. And so that in a final solution, you can basically omit the interactions with all those people, because the final result really depends on a smaller cluster. And this kind of clusterization, all these things are based on this quantum information theory stuff, and that's what we use also in quantum circuit simulation.
I would like to have a question to the beginning of this great talk. So you spoke about this maze runner algorithm to keep all of the cores busy, but how can you achieve that when the different tasks have different memory needs? For example, 2 tasks may collide, not fit into the system memory, or have an online problem and you don't know the access of to the data in advance. And for my personal interest, can you tell me that we can achieve this with high-level languages like Python? Okay.
So that the way that how it's an Andor, we talked about this, I'm pretty sure in the afternoon. That so originally the mathematics that we do, we write this in MATLAB or Python, because of course already programming subsidies. I have a code which is about 70,000 line long, so that it's full of math. So that it would be a nightmare to rewrite it in a different way. But all this prioritization issue, that's a C++ CUDA kernel that we are developing. So our codes are interfaced with our C++ module. In MATLAB, there is the so-called max interface, but you can do this also in Python, where you just simply pass the pointer structures and everything is done there. So that all the metadata which generates, so that if I go to this cartoon, then all the data generation here, these are on the MATLAB level. They generate and pack all the things. And of course, you transfer it, and then all the executors are really the C++ and CUDA kernels. You cannot do this in MATLAB and either in Python, because if you do this, then the highest performance that we got was around was around something like 4 or 5 teraflops. It's really extremely poor. Because this really requires all these sophisticated things, and none of these are included in all these languages and packages. So that they transfer the data, they execute something, and then you just recollect it. And then you have to do this millions of times, and the overhead is so huge that it kills completely the performance. And of course, I can show you these nice results, but this took years, because first we were up here, then we did something, and here you can also see this line. And there is this one, and we just call it new. So with the old code, this was the scaling, and then we worked hard, and we get this new one. That was basically this kind of hashing algorithms using different data sets and so on. So with this, if you just simply download these modules, you can do things, but it's extremely poor. We tried it in the very first time a couple of years ago, but we gave up. And then I'm having discussions with MathWorks every month, once a month. And I'm always complaining about the shitty implementations that MATLAB has, because if we can do this, then they could do it also. But anyway, they're always telling me that, oh, we are using MATLAB for something that is beyond their scope. So, okay, then that's it. But as I said, you can interface whatever development you do through these interfaces.
It's very fast. You showed me a two-dimensional example. What was the scaling for that?
This one.
Yeah.
Which system?
A 2D system.
That's a 2D system, and what is important is on torus geometry. So I didn't go into the details, but when you have a 2D system, then in a 1D system, these tensor network state methods are very good because you have these nearest stable interactions. You are happy even with long range. But once you have a 2D system and you map it into some tensor topology, then you introduce these long range interactions and long range stuff. So then it's a nightmare, especially if you close it and you put it in a torus. This is a killing factor. So nobody was ever able to do any, neither us before. Now, as I said, there is also something that there's a shift in here. So this is what is called the real space representation, but we also optimize the modes so that we also optimize the underlying basis. And together with this unitary optimizations, we get something where the computation cost increases because of this gets more terms in the Hamiltonian, but you get the same scaling. But what turns out that the original problem that you saw with this bond dimension, I don't know, 10,000 with SU2 symmetry, you can get the same with 256 in our new representation. And this 256, if you do it, you get also this performance. So the original problem that runs for almost a day, now you can do it, this is 10, so it's about 6 minutes.
Okay, so I think that's the point we have to stop right now. So let's thank Örs again. It was an excellent
Thank you for your attention.
And what we learned from this, that there's no free lunch in computing programming, but there is always free lunch on the GPU day. So I kindly ask you to prepare yourself. You can leave your stuff here. We will lock the things and everything is secure. So we will go together to the canteen. We have the lunch, and coming back here, coffee will be here, not there, but all the rest you can just follow my colleagues, choose one of us, and then try to move together. Okay, thank you very much, and let's back in time. The time is at 2 sharp.